We are at 2:02, and I'd like to welcome everyone to SMART's first webinar of 2022. Srikanta Mishra, would you like to introduce our speaker?
Yes, certainly. Thank you, Mia, and a very warm welcome to all of you. And to our speaker, Dr. Steve Zitney from NETL. He conducts process system engineering research under the Strategic Systems Analysis and Engineering Directorate, located in Morgantown, West Virginia. And he leads R&D efforts on the design, operation, and control of flexible integrated energy systems. Dr. Zitney has over 35 years of R&D experience and has authored and co-authored numerous publications, conference presentations, and book chapters. He also is a fellow of AICHE and is a trustee of the Computer Aids for Chemical Engineering Corporation. His topic, Virtual Digital Twin for Real-Time Integrated Power Plant Control Room and Field Operations, seems like it is a bit disconnected from what we are engaged in, but obviously there's a significant degree of overlap in terms of the similarity with the operational aspect of a CO2 injection project. And we're hoping to find lots of adjacencies and potential applications of the kinds of concepts that he has pursued in a power plant operational setting. So with that, it's over to you, Dr. Zitney.
Thank you very much, and good afternoon, everyone. Thanks, Srikanta, for the introduction and for the invitation to talk about virtual digital twins with the SMART initiative team today. Really appreciate the opportunity to discuss this virtual digital twin project, which I worked on for 10 years or more overall, and it involves coupling a high-fidelity dynamic simulator for a power plant with a 3D augmented reality, virtual reality plant environment. And we use this virtual digital twin for research, training, and education on flexible operations of power plants with CO2 capture. In preparing for today's webinar, took a look at the SMART webpage and the information, and I knew SMART was dedicated to subsurface applications and did a lot with machine learning. I was interested to read about the visualization platform challenge, and I see that you're putting together a software-based visualization platform that can take in subsurface data for analysis and visualization, and you're hoping to be able to use this platform in research, training, and education. So I think you'll see today there's some overlap and some nuggets you'll be able to take from my presentation on the capabilities and features, as well as the multi-phase development and deployment approach of our virtual digital twin. So let's start off with a bit of motivation, and in terms of key challenges facing the electricity sector or power generation sector. Probably many of you on the phone know that with the increasing penetration of intermittent renewable generators on the grid, so wind and solar, that it's forcing more conventional power generators, coal-based and natural gas-based power plants, to operate a lot more flexibly. So this is creating a number of new top priorities for the sector. So power generators are looking to improve plant performance during load following operations, so having to ramp the plants up and down to match the intermittent renewables. They're also trying to move their plants to lower and lower minimum load, so they don't have to completely shut them off, but they're sitting there idle waiting to catch price spikes in electricity. Then, of course, all this increased flexible operation is sometimes degrading and damaging equipment over time, so it's causing an increase in plant downtime and operation and maintenance costs. And in some cases, it's causing increases in environmental emissions as well, CO2, for example. And if we look above or beyond the plant gates to the grid, there's also a real need to strengthen grid resiliency and security under flexible operations. Now, if we look at the subsurface, which many of you are focused on, I see a lot of common motivating driving factors. You're looking to optimize above ground well operations, the injection and production rates, and you're also looking to manage the reservoir and the operations under the ground in terms of whether it's CO2 sequestration for storage or enhanced oil recovery. And you also have sort of health monitoring issues, trying to ensure no leakage from a reservoir, trying to limit induced seismicity. So I see both industries really, electricity generation and subsurface, with many common goals trying to get to sort of enterprise-wide optimization. So I see both industries looking to address all of these operational challenges via digitalization. So more and more use of advanced optimization and control techniques, an increase in the use of digital twins for physical assets, which is the focus of my presentation today. And most of you probably know there are various definitions for a digital twin. The most common one is a data-driven digital twin, where you're taking data from your asset or archive data to create the digital twin. There are also first principles dynamic models based digital twins, and that's the focus of my presentation today. So it's a high fidelity representation of the assets. And for many years in power generation, utilities have been using simulators, dynamic simulators, to represent their plant. And these models are parameterized, so you can solve parameter estimation problems to match your model to your plant, therefore having a form of a digital twin. And then the third category are the sort of the CAD-based virtual reality and augmented reality type digital twin models, and I'll also be discussing that today as well. And then next, we know with the increasing availability of cheap sensors that you can put pretty much anywhere. Now we're riding the wave of Internet 4.0 and data analytics, AI, and machine learning, and smarts is definitely focused in these areas. So with the increasing data, we're doing more condition-based monitoring, fault diagnosis, trying to figure out when we're outside our normal operating range when a fault occurs, not only identifying it when it's occurred, but perhaps get at the root cause analysis, and a move from reactive maintenance to more predictive maintenance, and just trying to do more in terms of overall asset performance management. Then if we look beyond just an individual assets or collection of assets like a power plant or just one storage well, in the case of subsurface, where you're looking to manage assets across an enterprise, organizations are applying more digital automation, intelligence, and interconnectivity across the enterprise, trying to move more towards enterprise-wide optimization of operations. So with that motivation, that backdrop, I just wanted to move into the rest of my presentation today, and you see the outline here. So I'll be focusing on a virtual digital twin for a power plant with CO2 capture, and it really contains two pieces: the dynamic simulator, which is deployed in the control room, and then the 3D virtual plant that represents the plant for field operations. So I'll talk about the features and capabilities of each of these pieces, and then the multi-phase, the development and deployment approach that we used here. And then I'll move into the application and use of the virtual digital twin for training, education, and research, and wrap up with conclusions and some comments on future directions. So before I get started with the rest of my slides, I wanted to show a short video to give you a feel for when I talk about virtual twin, what am I really talking about in the context of my presentation today. So I'll I'll play the short video, and you'll hear reference to an IGCC power plant with CO2 capture. So this stands for Integrated Gasification Combined Cycle, and that's the type of power plant that we were modeling here, and I'll talk about it in more detail a bit later. You'll also hear a reference to AVASTAR, and that acronym stands for Advanced Virtual Energy Simulation Training and Research. So when we deployed our virtual digital twin, it was at the AVASTAR Center at NETL. Since then, we've sort of moved the term AVASTAR over to West Virginia University. We also deployed the same virtual digital twin there. So they're doing most of the training using this digital twin and are using the name AVASTAR. So I'll start up the video here. It's about 2.5 minutes long, and hopefully it'll give you a feel for the virtual digital twin that I'm discussing today.
NETL's Advanced Virtual Energy Simulation Training and Research, or AVASTAR Center, is designed to promote operational excellence for the nation's energy systems. From smart power plants to smart grid, the AVASTAR Center brings together advanced dynamic simulation and control technologies, state-of-the-art simulation-based training facilities, and leading industry experts to focus on the optimal operation of clean energy plants in the smart grid era. The AVASTAR Center houses a high-fidelity, real-time dynamic simulator for an integrated gasification combined cycle, or IGCC, power plant. The IGCC Dynamic Simulator is designed as a full-scope operating training system that enables control room operators and engineers to experience how the plant will operate under almost any scenario and condition. The AVASTAR Center also offers a first-of-a-kind 3D virtual immersive training system for use in plant familiarization and walkthrough, as well as interactive training of field operators. By fully integrating the real-time dynamic simulator with virtual reality-based immersive training systems, the IGCC training scope covers both control room and field operators, providing full plant crew training. AVASTAR facilities, dynamic simulators, and other resources are available to NETL RUA researchers and university students, enhancing results through collaboration on plant operations, control, and safety for advanced energy systems. Clean energy plants with carbon capture are extremely complex and highly integrated, requiring advanced automation and control technologies, as well as skillfully trained personnel to operate what are effectively combined chemical processing and power plants. The AVASTAR Center benefits the energy industries by enabling utilities to optimize the operation of their power generation systems for increased efficiency, lower cost electricity, and more efficient removal of carbon dioxide. Achieving operational excellence for commercial scale capture processes can have significant impact on the extent and the rate at which they will be scaled up, deployed, and used in the years to come.
Okay, hopefully the short video there gave you a better idea of the type of virtual digital twin I'll be discussing today. So as you heard in the video, the specific application we were looking at was IGCC Integrated Gasification Combined Cycle. And IGCC plants are really two plants in one, a chemical plant and a power plant. On the chemical plant side, we have the gasification, so you have a gasifier here that's gasifying coal at high temperature and pressure, whereas a conventional power plant is combusting coal, but we're gasifying it at high temperatures and pressures using high purity oxygen from an air separation unit. It produces a synthesis gas, mainly carbon monoxide and hydrogen. That syngas is cleaned up, it's shifted with a water gas shift to hydrogen and more CO2. The CO2 is then captured using a physical solvent, pre-combustion CO2 capture. The CO2 is compressed, and that leaves us with a hydrogen-rich syngas then that we send to the power plant, the combined cycle, where power is produced in a couple of gas turbines, which we then recover some of the heat to produce steam that's put through a steam turbine to produce even more power. So the motivation for developing this IGCC virtual digital twin is that IGCC plants are known for flexible technology for clean power generation, especially for coal-fired plants when you're looking to capture the CO2. So these plants are fuel flexible. They can gasify not only coal, but petroleum coke and biomass. And so in our simulator, we would often co-fire biomass with coal, for example. These plants are also product flexible. They're polygeneration plants. They produce not only power, but once you produce the syngas, you can use it to generate hydrogen and chemicals, for example, when electricity prices are low. So even in today's environment, when we're moving again towards hydrogen, these plants are relevant. So our digital twin had CO2 capture and compression, as I mentioned. So we compress the CO2 up to sequestration pressures, but that's the boundary of our virtual digital twin. But during the course of our project, we did consider and discuss looking at the entire CO2 life cycle. So adding on dynamic simulation for the pipelines, the transport of the CO2, the above ground injection equipment, and then perhaps even using fast surrogate models for the CO2 sequestration piece, although we never ended up sort of pursuing all of that, but we did have discussions along those lines. The main justification for developing this virtual digital twin was that at the time, back in 2006 when we were starting up, no IGCC plantless CO2 capture existed. There were a couple of IGCCs in the U.S. Actually, they were DOE-funded projects that had been running for 10 years. One of them, you can see here in the lower right, was the Tampa Electric plant down in Polk County, Florida, and there was also an IGCC in Wabash, Indiana. So there was a real need for demonstration, training, education, R&D on the operation and control of IGCC plants with CO2 capture. So that was a motivating factor for the development of this virtual digital twin. At the bottom of the slide here, I'm showing a book chapter. It's probably the best overall summary of this whole project. I'll have my contact information at the end of the presentation. So if you're interested in getting a copy, I can send out a copy of the book chapter. Okay, just like SMART, this project was a collaborative effort, multi-phase, multi-year, multi-organization. So it was NETL-led and funded. Most of the funding came through NETL's gasification program and about 5% from the CO2 capture program. Since this was a multi-million-dollar virtual digital twin, we had to have a competitive procurement. So we put together a detailed functional specification for the simulator along with all the process descriptions for the plants. It was a very large plant, about 20 major plant sections. Then we put that all out in a request for proposal, got proposals in, evaluated them, and awarded the project to a software vendor, and I'll talk a bit more about that coming up. Now, while we were starting the Virtual Digital Twin Project, NETL's Regional University Alliance, or RUA, was ongoing. You heard that perhaps mentioned in the video, and West Virginia University was one of our partners. And for about 3 years before this Virtual Digital Twin Project, we had been working with them on IGCC dynamics and control. And so we used a lot of that work to do due diligence on all the modeling that was being done for this project to help add fidelity to the digital twin for the gasification section, CO2 capture, the air separation unit. And we also had a group of industry stakeholders, and you can see some of them listed on the bottom here that helped guide and direct the project. So once again, just to reiterate here, the virtual digital twin I'm discussing here involves coupling a high-fidelity dynamic simulator with VR and AR technologies. So the dynamic simulator is deployed in a control room type of environment, and users or operators interact with it through operator interfaces or human-machine interface HMI displays, they're called here, and you can see one shown here. And for our IGCC plant, we have about 150 screens representing the whole plant. And so overall, this system is also known as an operator training system, or OTS. So you'll hear me refer to it as an OTS going forward. And so the OTS is connected live and in real time to the 3D virtual reality-based walkthrough environment. And it's also known as an immersive training system, or ITS. And the ITS is a nice standalone tool that can be used for plant familiarization, but I think the real power comes in with its real-time connection to the high-fidelity dynamic simulator, having that running underneath the hood, and I'll sort of stress that point a bit more later in the presentation. So now I'll talk about both the OTS and ITS capabilities and features and the development. So in terms of the capabilities and features of the OTS, as I mentioned, based on first principles dynamic model, so heat material balances for the whole plant, all the thermo reaction kinetics for the gasifier, for example. It's a very high fidelity model, so it can be used to look at normal steady state full load conditions, but can be used to look at startup and shutdown as well. What happens during transients? How do you ramp the plant up and down? You can introduce disturbances. And the full electrical system is also modeled for the whole plant up to the connection to the grid. So you can connect it to a real-time grid simulator, for example, and you actually have to sync up the turbines in the plant to the grid. All the process controls are modeled in software, the regulatory low-level controls all the way up to plant-wide coordinated controls for connection to the grid. And our OTS is known as an emulated OTS because all the controls are modeled in software. You can actually have a stimulated OTS where the controls are actual hardware, an actual digital control system. And this is often used in the power industry for doing control system checkout before the controls are used in the plant. They're tested out on a simulator ahead of time. We get real-time performance out of the simulator. That's required for the training. And we get that real-time performance using dynamic engines that run in parallel on multiple core machines. So we can run up to about 2.5 times faster for this large-scale plant. All of the dynamic data that's passed back and forth between the dynamic simulator, the HMIs, between the dynamic simulator, the ITS, are all done using industry standard interfaces, OPC, OLE for process control, unified architecture, UA. So it's a full scope OTS, has all the human machine interfaces, HMIs, and you can see an example here in the two figures in the bottom. Full trending, so any variable can be, you can plot it out over time. Full alarming, both audible and visual. In a normal power plant, you have the alarm screen up in the front of the control room. Same thing in our control room, we have the alarm screen up at the front there. You can malfunction any piece of equipment in the plants in a host of different ways. There's a data historian saving all of the data, so you can save a snapshot of the current plant conditions at any point, so you can rewind back to a certain point if you want to stress a certain training situation. And there's a full trainee performance monitor as well, a TPM system where an instructor can evaluate operators and score them, produce reports. So it's good for educational purposes as well. So we use a multi-phase development and deployment approach, the 5 major phases shown here. So phase 1 was the initial scoping study. We worked for about 6 months on the scoping with the consultant here. So we developed all the simulator requirements, the features we wanted, the level of fidelity, identified potential partners, the milestones, deliverables, cost, staffing, and schedule. And once we got approval to move ahead, we entered planning phase. And this is where we developed the detailed functional design specification for the simulator that we put out in the request for approval. And once the project was awarded to a software vendor, we entered phase 3, which was model development and validation. And if you remember, I said at the time an IGCC with CO2 capture plant didn't exist. So in this case, we had to design the whole plant and all the controls. Typically, when an OTS is developed for a plant, it's for an existing plant. So we have to design all the controls. So it was a bit different here. So we had to develop all the process and instrumentation diagrams, all the equipment sizing, develop all the controls. And then we validated the model at its full steady state design point, so full 100% load based on some NETL baseline studies. And the rest of the dynamic model validation, which I'll discuss later, was done using testing by actual industry experts. We had to develop all the HMIs. I mentioned we have, I think, about 150 of those, all the operating procedures for startup, shutdown, all the alarms, malfunctions. And then phases 4 and 5 are the testing phases. So you do factory acceptance testing at the vendor site, and then final site acceptance testing, which was done at both NETL and West Virginia University. Moving on to the 3D virtual ITS, there we were developing the virtual plant model, so all the CAD. So we started with all the process and instrumentation diagrams and developed the 3D CAD. And then we went out to plants and took thousands of photos to wrap the 3D model to give the photo realism. So we went to the Wabash, Indiana IGCC plant, to a CO2 capture plant and several other plants. So as you saw in the video, in terms of the immersive piece, you have an avatar that represents a field operator that you move around the plant using a standard gamepad type controller, and you can interact with different objects within the plant. So the operator can open and close a valve, start up and shut down a pump. So there's full collision geometry sound. So when you start up a pump, you can hear it running. We can bring up variable trends and web pages in the virtual environment, which is great for training purposes. Then in addition to the virtual reality, we also implemented augmented reality. So you saw you can make equipment items transparent and even add in animation. So for example, here for the CO2 capture column, and the important point here is that all the animations in the virtual plant are tied back to actual dynamic variable values from the OTS. So the liquid level holdup on the trays, the animation of the vapor traffic up the CO2 capture column are all dependent on the actual dynamic variable values in the simulator. Same thing for the animation of the gasifier. The look and feel of the gasification fireball here is dependent on gasification efficiency in the OTS, and the look and feel of the slag flow down the refractory walls of the gasifier, how it looks, the speed is tied to slag viscosity in the simulator. So that gets at the point of having the power of having the ITS connected live and in real time to the dynamic simulator. You can also introduce virtual malfunctions in the 3D plant, like liquid leaks, gas leaks, fires, and again, these are tied to the dynamic simulator in the control room as well. So if you have a liquid leak, not only do you see it in the virtual environment, there's some impact on the flows that a control room operator can pick up on as well. So an instructor can introduce a malfunction and see who picks up on it first, somebody in the control room or a plant field type operator. So overall, very powerful system for joint control room and plant field operations testing. As far as the multi-phase development approach, same 5 phases here. The only difference, the major difference is phase 3, we're developing the CAD-based 3D virtual model and all the content there. So all the animations, place the valves, the temperature gauges, pressure gauges, and so in terms of testing, it was a bit different here too. We were tracing all the piping runs between the plant sections, making sure the 3D matched our process and instrumentation diagrams and so on. So a lot of testing for the ITS. But the vendor, since then, they've gone on and automated a lot of the testing procedures now since we undertook this particular project. So in terms of development partners, I already mentioned West Virginia University, WVU. URS, NETL's main site support contractor, was also involved. And in terms of the software vendor, the project was awarded to Aviva Schneider Electric. So Aviva was their software arm. So we used Aviva software, DynSim for the OTS, InTouch for all the operator training interfaces. In fact, InTouch is probably used in about 35% of the power plant control rooms in the world. And for the 3D virtual plant, we used their iSim package. And we were their first large-scale plant-wide project using iSim, and we ended up winning an R&D 100 award for this iSim-based virtual digital twin. Fossil Consulting Services was our main training partner. So when we had to give, we have to give long, week-long, 2-week-long courses. FCS gives those, and they're power plant training experts. They were also a development partner and helped put together the functional design spec for the simulator. EPRI, the Electric Power Research Institute, was also a development partner. They helped a lot with the combined cycle, the power plant portion of the plant. And it was through their coal fleet program that we brought in the industry stakeholders that I showed previously. Then CH2M Hill was an IGCC expert company that was brought in through Aviva Schneider Electric. Now, for testing partners, I mentioned the dynamic model validation. We did a lot of that through testing with experts. So we brought in engineers from Air Liquide. They put the air separation unit through its pieces, started up, shut it down, introduced malfunctions, and just to make sure everything was looking right there. Same thing, we brought in a couple IGCC consultants and operators. So they started up the full plant and shut it down, ramped it up and down, and same thing with several gasifier experts as well. In terms of the overall length of the project, from scoping all the way through testing, for the OTS dynamic simulator, that was about 2 years of effort. And there are several reasons for this. A typical power plant simulator for an existing plant takes about 9 months to a year to complete. But if you remember here, an IGCC with CO2 capture didn't exist, so we had to do the full plant design, develop all the controls. Plus, the IGCC is really almost 2 operator training systems in one. In fact, that's the way we developed it, the way we tested it. So the gasification, CO2 capture side of the simulator was developed down in Aviva's Houston offices. The power plant side, the combined cycle, out in California. So we did separate FATs at each site. We integrated the simulator into the overall IGCC. And did final testing down in Houston. The immersive training system took about a year to develop, and it lagged the OTS by about 1 year. Then finally, we deployed the virtual digital twins at NETL and WVU and did final site acceptance testing there. A few words on the facilities and equipment for both NETL and WVU. So we deployed the virtual digital twin building B2 at NETL in Morgantown. It's primarily used for research. We deployed it at WVU at the NRCCE, National Research Center for Coal and Energy, at the Avistar Center there. So it's used for research, education, and training. Both facilities dedicated 2 rooms to the virtual digital twin, one representing the control room, one for the virtual plant. Each facility has its own local area network for running the simulator. So for the OTS, I guess overall we have about 20 computers. For the OTS, 8 operator stations. You can see in the 2 middle photos here, the operator training stations around the front of the room, a couple of instructor stations in the back of each room. So this is where the instructor sort of runs the show, the overall simulators, observing the operators, perhaps introducing malfunctions or going through operational scenarios. The model servers for running the overall power plant simulator are back here. So these are big multi-CPU machines, and we have a couple of engineering stations as well for model development. For the virtual ITS, 2 high-powered graphics workstations. So we could have 2 different teams of field operators working in 2 different parts of the plant at each facility. And there's also an instructor station for the ITS that deployed in the control room. So one instructor can observe the operators in the control room, but he also had a window into the room next door into the field operations and could lock on to a field operator and watch what field operators were doing. And that's another thing in the ITS, all the video is recorded, so you could go back and review it for training purposes. And as you saw in the video, we use 3D projectors with the virtual glasses, and the system also runs with head-mounted displays. For example, we were using originally Oculus Rift head-mounted devices. So with that, let's move into the actual application and use of the virtual digital twin. So we used it in industry workforce training. So we provided hands-on digital twin-based experiential learning using experienced power plant trainers, and we provide courses from basic orientation to advanced operation courses, and you can see some of the examples of the training sessions that we've provided over the years. So did training for NTL's gasification program course, for EPRI coal fleet members, for the Gasification Syngas Technologies Council. It's the main gasification advocacy group in the U.S. For NETL's carbon capture simulation initiative, so we focused on the capture piece of the plant. We provided 2-week-long training courses on the combined cycle for an integrated energy company in South America. Then we did a lot of training with the China Wanang group when they were developing their GreenGen IGCC plant in China. We also teamed up with a regional community and technical college. They had a 2-year power plant, or have a 2-year power plant training program where they're putting through cohorts of 20 students that receive classroom training, simulator training, and then on-site training at regional power plants. So we had a memorandum of understanding between NETL, the Community Technical College, and WVU, and provided training at WVU. So we trained their trainer. You can see him at the front of the room and the photo at the bottom there. And then he trained the students, mainly on the back end of the plant, the combined cycle part of the plant. So this whole program, again, was used to develop a well-qualified workforce and to place these students in power plants in the region. The virtual digital twins also used for chemical engineering education at WVU. So it's used in the semester-long process simulation and dynamics course, so the students get hands-on use for the simulator. Also used in the process control course, so they're focusing more on the controls there. And it's also used in their senior process design course. So they use a simulator a bit and also focus on the virtual plant. Back in the day, when I was a chemical engineer, a lot of times, sometimes you got to a plant field trip that's really not done anymore. So the ITS is actually a good tool for that, because the IGCC is a chemical plant, power plant. So the virtual ITS gives the students really a good feel for just how massive one of these facilities are. I mean, in their books they're usually dealing with 2D flow sheets in a book, and it really doesn't give them a feel for an actual plant, whereas the digital twin does that, and they can walk up to the gasifier platform, for example. This thing's 8 stories high, and they really get a feel for how large one of these plants can be. Now at NETL, we primarily use the virtual digital twin for research, mainly on flexible operations. So we were looking at the flexible operation of IGCC. So we ramped the plant up and down, look at what was limiting, ramping. And so we did a lot of work on model predictive control strategies for improving the flexible operations of IGCC in terms of the gasifier, especially the air separation unit, CO2 capture. And we do a lot of research on more futuristic controls. So we do a lot of work on biologically inspired controls and applied it to the digital twin, the CO2 capture portion, to provide better set point tracking for maintaining that CO2 capture at the target 90% capture rate during various plant transients. Even though this is a first principles digital twin, we do work on machine learning based surrogate models and make use of those within the simulator. I know SMART has focused a lot on machine learning. So our surrogate models are not data from an asset, but usually based on higher fidelity models, so multi-dimensional partial differential equation models or computational fluid dynamics. So, you know, your reservoir models, if you want CFD. So we do similar type of work here, mainly for the gasifier and CO2 capture. We also do a lot of health modeling. I mentioned ramping these plants up and down could cause equipment degradation, and one of the key issues for IGCC is degradation of the refractory within the gasifier. The gasifier is a very expensive piece of equipment, and the refractory can degrade. So we did detailed mechanistic modeling of the refractory, the slag flow down the refractory and penetration into the refractory brick. And then we developed operational control strategies to not only maximize gasifier performance, but also trying to minimize degradation of that refractory. Another important area of research using the virtual digital twin was optimal sensor network design. So when we developed the virtual digital twin, we placed all the sensors, so the thermocouples for temperature, the pressure gauges, the flow meters, that was all done using expert knowledge or rules of thumb. That's how we did it in our simulator, and that's how typically done in industry. But we're working with WVU on rigorous dynamic optimization-based approaches to synthesizing an optimal sensor network with respect to some objective. So you're really looking to gather intentional data, maybe to improve plant performance, do a better job at rejecting disturbances, estimating variables that you can't measure. For example, in the gasifier where you have very harsh conditions, to place your sensors to do a better job at condition monitoring, fault diagnosis, and even useful for data-driven digital twins. Where should you place your sensors to get the best data that you need to develop, you know, a good digital, data-driven digital twin for your asset. So the graphic on the bottom there just shows results of one of our optimizations in terms of placement sensors for the CO2 capture. We also made use of the simulator for some work on a natural gas combined cycle plant. We had an industry partner plant where their IGCC was doing a lot of ramping up and down. So we leveraged the back end of our IGCC, the combined cycle, which we start up on natural gas before switching over from syngas firing anyway. And we went out to the plant, got information on their design, operating procedures, operating data to match our model to the plant, and worked with them to improve their operational procedures, try to reduce temperature gradients during cycling operations, especially in the heat recovery steam generator part of the plant. So with that, I'd just like to move on to the final concluding remarks. So we all know the era of digital transformation is definitely accelerating. So is the industrial use of virtual digital twins. They're being used to try to improve plant performance, reduce downtime and operation maintenance costs for workforce training and education. At NETL now, a lot of our dynamics and control work is aimed at flexible integrated energy systems. So co-production of power and hydrogen with CO2 capture, with and without storage, thermal storage or hydrogen storage. And a lot of our dynamics and control work is being done under the umbrella of NETL's Institute for the Design of Advanced Energy Systems, or IDEAS effort. So here we're doing a lot of dynamics control and health modeling, along with optimization, including dynamic optimization. We continue to do a lot of work on machine learning-based surrogate models, and we're also moving beyond sort of the plant gates and coupling our power generation models with grid models to look at integrated generation and grid market dynamics, and how do these integrated energy systems perform in the energy market. In terms of future applications for virtual digital twins, I see one area of increasing use is for cyber physical systems, so combining the software-based digital twin with some actual hardware. NETL has some activities there in NETL's Hyper facility looking at gas turbine fuel cell hybrid systems. So we have high-fidelity dynamic models for solid oxide fuel cells connected to an actual gas turbine and balance of plants, and looking at operational and control issues for these gas turbine fuel cell hybrids. Another area of active research is the development of hybrid digital twins, so combining first principles and data-driven machine learning-based twins. And actually in the literature, in reviewing this, a lot of the work in this area early on was actually in the Subsurface, and a couple of the leading companies there working on hybrid digital twins. And the final area is cybersecurity. Virtual digital twins could be used there. One of the big issues is if you have a plant disturbance or something going on in the plant, trying to determine whether it's just a process-related thing or something related to a cybersecurity threat. So digital twins can really help out there. And actually, GE is doing a lot of work in this area for power generation. In fact, their virtual digital twins for cybersecurity are known as digital ghosts. So with that, I see a lot of potential good uses for virtual digital twins, so database, first principles models, the virtual reality, augmented reality models in both the electricity generation sector as well as for the subsurface. So with that, I'd like to thank you for your attention. So you have my contact information here where you can email me if you have any questions or want that book chapter. And also I want to put a plug in for IDEAS, which is our major sort of process systems engineering effort these days. There's our webpage there where you can look up some more information on that whole initiative. So with that, again, thank you, and I'd be happy to try to answer any questions.
Thank you very much, Dr. Syste, for a fascinating presentation. Lots of food for thought with respect to which of these elements we can leverage as we move on to the next phase of SMART. And maybe we'll keep bugging you with questions about connections and tools and techniques. So let's open it up for questions. As always, please use the raise hand button, and then Mia will call each one of you to ask a question. So I'd like to get the process started. You mentioned that these are real-time dynamic simulators, meaning that you are using the appropriate mass energy balances and ordinary or partial differential equations. And so the computational time is not burdensome to the point that you don't have a need for fast proxy models.
That's correct. So the IGCC simulator, to get the real-time performance, we used parallel dynamic engines. So we had about 16 dynamic engines running on multiple core machines in order to get the real-time performance. And the solution approach We use a special solution approach, simultaneous modular, where we're solving the pressure flow equations sort of at one level and the underlying unit model equations at another level, but we are able to get real-time performance. That's an absolute requirement. So when I say real-time here, the time step in our simulator is about a quarter of a second time step, and that's fairly typical for the dynamic simulators operator training systems that are developed for the process industries in general. Now, you can go to much faster time steps. I mentioned our hyper facility where they're looking at cyber-physical systems, and their time steps, they're looking at microseconds, so much faster. But so when I say real time here, our time step's about a quarter of a second, and yes, we are getting real-time performance with these first principles models. So our gasifier, we use sort of a multi-zonal approach there with 4 reaction zones, but we have all the detailed kinetics. So it's tough to get real-time performance there. That we use rigorous distillation columns for the CO2 capture, which is challenging for real-time performance. But yeah, the solver technology helps with all of that as well.
Okay, thanks. Over to you, Mia.
All right, I'm looking for any raised hands, and participants, you can also use the chat box as well.
I have a question. This is for Ramzada. I really enjoyed the talk. It was excellent. And I can think of many leveraging opportunities with our SMART program. I have a technical question. Did you use any fuzzy controllers in your design and the operation of your with digital twins?
No, we didn't look at fuzzy control at all. I mean, all of our regulatory controls are the standard PID controllers, proportional integral derivative controllers, but we, as I mentioned, did have an overall coordinated control system, so higher level controls above the regulatory control layer, and that's used for ramping the plants and when it's in automatic generation control in connection to the grid, so it can match some load following profile that it's getting from the grid. But in terms of controls research, most of our efforts are in model predictive control, working with WView on actually reinforcement learning augmented model predictive control techniques. We haven't used it in connection with the digital twin, but on other dynamic models, we're working with a regional power plant, where one of the control challenges during flexible operations is NOx control in the selective catalytic reduction unit in this pulverized coal plant. So we were looking at reinforcement learning, augmented model predictive control strategies there.
Yeah, I might want to communicate with you offline, but in this CO2 injection, there is a potential optimization to use fuzzy controllers so that the off and on aspect of injection can be controlled using fuzzy logic. So I'll discuss this with you separately.
Okay. Yeah, it's a common use control approach, I mean, across the process industry. So yeah, there's a lot of interesting things that could be done with fuzzy control logic. And that's another thing for our virtual digital twin. We have developed all that control logic and all the words escaping me, all the permissives, for certain permissives that have to be met before a certain pump can be turned on, for example. So all of that was coded up in this virtual digital twin. So it was it's a very realistic digital twin. And like to start up the plant in software, it takes 4 days to start up this huge plant. And I mean, that's pretty much how long it takes to start up in real life too. It's amazing. Once we got the simulator in place, it opens up all kinds of doors for optimization. Once you start optimizing it, I mean, you can come up with ways to optimize the process. In fact, when we were developing it, and once we were able to start, simulations, we'd come up with optimization ideas. Go to the vendor. Oh, can you add this or implement this? And eventually, it has to push back. We're not trying to, develop an optimal IGCC plant here, but this shows the power of really dynamic simulations and virtual digital twins. When you can, operate, you can even come up with, opportunities for optimizing design through, being able to operate the plants.
Thank you.
Mm-hmm.
Any other questions or observations to share?
Yeah, I just want to say I'm looking forward to following SMART now. Like I said, I read up on the visualization platform challenge and see if, coming out of phase 1, going to phase 2. So be interested to see sort of the visualization platform and tools that come out of, that whole effort.
Likewise, and once again, thanks very much for taking the time to be with us today, Dr. Zitney, and very fascinating and enlightening presentation. And as Fred said, we will probably be in touch with you about, leveraging and building on some of your work. So thanks.
Thanks.
And bye, everybody.
Thank you.
We shall be in touch.
Okay, thanks, Mia.
Thanks, Mia.
All right. Take care, everyone.